In this lesson, we're going to cover NumPy. Basically, this lesson is called Introduction to NumPy by Maxwell Magnaut. NumPy really is an incredibly powerful package in Python, basically that is used right throughout the Quantopian platform. It has a strong integration with pandas and other tools that will be covered in the lecture series. NumPy adds support for multi-dimensional arrays and mathematical functions that allow you to easily perform linear algebra calculations. This lecture will be a collection of linear algebra examples computed using NumPy. So the first thing we're going to do is import NumPy as NP, that's the common short form for NumPy. We are also going to import matplotlib. This is really for visualization purpose. This is how you import it, matplotlib.pyplot as plt. So looking at basic NumPy arrays, the most basic way that we could make use of NumPy in finance is calculation of the mean return of a portfolio. Now say that we have a list of that contain the historical returns of several stocks, which is this one here. Let me just run these cells. In this list, what do we have? We have 1, 2, 3, 4, 5 returns, and we're gonna just store all of these, store this list into stock list. We can make an array by calling a function on the list by storing numpy.array and store this into returns, and then we print the returns out as well as showing what the types. The data types is. So it shows that the returns is same as the list, except this time around the data type is actually a NumPy array. Now you'd notice that the type of array is ND array, not just array. This is because NumPy arrays can be created with multiple dimensions. If we pass np.array, a list of list, it will create a two-dimensional array. If passed a list of a list, it will create a 3D array and so on and so forth. If we store the NumPy array 1, 2, this is a list, this is another list, and 3, 4, and store this NumPy array into A, and we print it out, notice that it's actually a two-dimensional array and the type is a NumPy array. We can access the dimension of an array by looking at its shape member variable, so you just need to print the variable name a and then using a dot method and shape, and you notice that is actually a 2 by 2. Arrays are indexed in much the same way as lists in Python. Elements of a list begin indexing from 0 and end at n-1, where n is the length of the array. Now if we print the returns, bracket 0, so we're indexing the first one, and the returns of the length -1, which is the last one. If we scroll up here, this is the returns. The returns look like this. Basically 0 here is pointing to the first one. Length, which is n, -1 really refers or point to 4.2, so that's why you have the results of 3.5 and 4.2. We can take a slice of an array using a colon, just like a list. So if we print returns from 1 to 3, basically we are pointing to 5 and 2. Right. A slice of an array, like a list, will select a group of elements in the array, starting from the first element indicated and going up to, but not including the last element indicated. It's exactly the same as a list. In the case of multi-dimensional arrays, many of the same conventions with slicing and indexing still hold. We can access the first column of a 2D array like so as well. So since this is a 2D, this basically refers to all of it. Colon means everything, 0 means we are pointing to the first. So if we look at the 1, 2, and 3, 4, which is A. So really we're actually slicing this column here. This is pointing to the column, and this is pointing to the so-called row itself. So we want all the row and only column number 1. So the way that array, NumPy array is row first, then column. And the first row of a 2D array like so, we put down 0 really is first row, and then column, meaning we want all of the contents at that row itself. So remember, this is the row, this is the column. Notice that each slice of the array returns yet another array. So if we print the type of this, we get a NumPy array. Passing only one index to a 2D array will result in returning the row. Okay, so we are only getting back the row within the given index as well, providing us with another way to access individual rows. So that's really A0, meaning we're looking at row number 1. Accessing the index of an individual element will return only the element itself. So A11 will only give us the element itself. Okay, let's look at array functions. Functions built into a NumPy can be easily called on arrays. Most functions are applied to an array element-wise, as scalar multiplication is. For example, if we call log on an array, the algorithm will be taken of each element. So basically, the log functions will be applied to each individual element itself. So when we do a numpy.log function, so this is the array function, so it will actually calculate log for all of these 5 individual element itself. Some functions return a single value. This is because they treat the array as a collection, similar to a list, performing the designated function. For example, the mean function will do exactly what you expect, calculating the mean of an array. So np.mean basically calculate the mean of all of the returns itself. Or the max will return the maximum element, so you always need to put an np dot in front to calculate the maximum. So for further reading on the universal functions in NumPy, check out the documentation by clicking on this. It will actually point you to the documentation itself. So the next we're going to look at return to the returns. Now let's modify our returns array with scalar values. If we add a scalar value to an array, it will be added to every element of the array. If we multiply an array by a scalar value, it will be multiplied against every element of the array. If we do both will happen. So let's do this. So taking the returns from previously multiplied by 2 plus a scalar value of 5, you notice that it will be multiplied by 2 first and then add 5 to it. NumPy also has functions specifically built to operate on arrays. Let's take the mean and standard deviation of this group of returns. So if we print, basically this is the text mean within the actual apostrophe itself, means colon. So this is the actual calculation itself, numpy.mean of the returns, and again this is the comment, standard deviation, this is the calculation itself, numpy.std returns. That gives you the mean being that and the standard deviation being that. So let's simulate a universe of stocks using NumPy's functions. First, we need to create the array to hold the assets and returns that we will use to build a portfolio. This is because arrays are created with a fixed size. The dimension can't be changed without creating a new array. So here we are looking at n is equal to 10. Assets is numpy.zeros n, which is a dimension of 10, comma 100. So basically we're looking at 10 rows and 100 columns. And the returns likewise is 10 rows and 100 columns. The function zeros is a built-in function, creates a NumPy array with the given dimensions that is entirely filled with 0. We can pass a single value or a tuple of as many dimensions as we like, passing the tuple n, 100 return a 2-dimensional arrays with n rows and 100 columns. Our result is a n times 100 array. Now we will simulate a base asset. We want the universe of stocks to be correlated with each other, so we will use this initial value to generate the others. Okay, so if we take a look at this, this is just the variable name, np.random.normal. Okay, we want to generate 100 random numbers, but it's normally distributed. Okay, so we have, this is the mean, this is the standard deviation, and the returns of this is stored as basically r_1 itself. The assets is the cumulative products of r_1, which is the variable we created here. Now the random module is in NumPy is exceedingly useful. It contains method for sampling from many probability distributions, some of which are covered in the random variables lecture in the Quantopian series. In this case, we draw n is equal to 100 random samples from a normal distribution with the mean of 1.01 and standard deviation of 0.03. We treat these as the daily percentage returns of our assets and take the cumulative product of these samples to get the current price. Now, the way we have generated our universe, the individual Ri vectors are each one-dimensional arrays, and the returns and assets variables contain 2-dimensional arrays. Above, we set the individual row of both returns and assets to be the first Ri vector and the cumulative assets price based on those returns respectively. We will now use this base asset to create a few other random assets that are correlated with it. Right, so what we're gonna do here is that we're gonna generate assets that are correlated with the Ri. Okay, so we're gonna use the for loop. Okay, so we're gonna use R1. Okay, which is this asset here. Ri really is a new asset. Okay, and we have random normal distribution. Okay, we're generating another 100 with the mean of that and the standard deviation of that. So in essence, this is to add into this. Okay, and for each one of these, we store it into the returns and index into I. So basically we have 1 to n, and in this case here is 100. So we're gonna generate 100 assets basically with normally distributed assets. So basically we are storing the returns, what we generate here using this formula here. Basically in essence, by and large, it's based off this. The so-called mean is 1.01, and this is very, very small. So in essence, it's gonna be very, very closely correlated in terms of the returns. It's just shifted up by a little bit, which is by 1%, well, 0.1% really. And the standard deviation is fairly high, so it's gonna fluctuate around. So in essence, we are actually generating the returns, 100 of them, based on this n, and just gonna keep repeating it and store all of this into the assets itself as well. This is the cumulative product of it. So the mean returns will be calculated for the whole R. So first of all we calculate the returns. Okay, mean returns of R, and then minus 1 multiplied by 100 for R in returns. So what does this mean? This is actually what you call a list comprehension. So we have returns. Okay, what is returns? That's this one here. So we are going through and extracting them out one by one. And then for each one, which is this one here, remember each R has 100 returns. Okay, it was generated from here and is stored into this. So each and every single row has 100. We calculate the mean, minus it by 1, and then multiply by 100. So in essence, this is really calculating the actual percentage returns. And the return volatility really is the same way, just calculating the standard deviation using the NumPy. So in summary, here we generate the remaining n-1 as securities that we want in our universe by adding random noise, which is R1, this one here. This ensures that our n-1 other assets will be correlated with the base assets because they have same or have some underlying information that is shared. Let's plot the mean returns of each assets and see what it looks like. So we are plotting the returns, and we X label the X-axis as stock, Y label as the returns, and we print the title for how many random assets. So when this is printed out, okay, what you can see here is the returns fluctuates from around 0.3 all the way to 0.8 something. Okay.